which we only touch very, very cursory in the interest of time. But and perhaps a little more importantly, we will focus on radiometry and photometry. This is important from the perspective of your projects, but also, this topics could be in the midterm as well. By the way, we haven't made the midterm yet, so it is possible there. I can't tell you one way or the other. Okay, why is this? Oh no, sorry. Yeah. So let's start with this. So of course, what we are mostly interested in is the idea of a heat engine, as I talked about before, because interestingly, even a solar cell can be thought of as a heat engine, and we'll come back to this concept later on again and again. But in the previous few lectures, you've seen that we talked about trying to create a hot region and a cold region and utilizing the difference between them to do some work. This is really the fundamental abstract idea of what a heat engine is. So, of course, more than 100 years ago, the idea of the steam engine is a good way to think about this, right? So you have a hot region where you are inputting the heat that converts the water into steam, and the steam essentially performs the work on the piston to push the wheel. And of course, it cools as it does the work. Because why does it cool? Because steam expands, the pressure drops, pressure volume curve, temperature cools, and it condenses, becomes water again, then heats up again. So that's the cycle. And then there's work is done. So the key concept to keep in mind is that the difference between the temperature of the hot part, T1, and the temperature of the cold part, T2, the temperature of the hot part is T2 minus the temperature of the cold part is T1, represents the achievable efficiency of the system. And we'll come to this idea of the Carnot cycle shortly. Now, this is true generally. In other words, we can be talking about coal plants, nuclear power plants, solar thermal plants, geothermal plants, thermoelectric devices, solar cells, whatever. So it's true generally speaking. Now, the most common heat engine that you are all very familiar with, but let's review in the in the interest of completeness, is the internal combustion engine. So let's just see very, very briefly how this works. It's a heat engine. Essentially, there's a chamber that you can see. So there are 4 steps here. There are 4-stroke cycle in this example, right? So in the first step, you're pulling in the air fuel mixture into the chamber. This is the intake part of it. So the piston is going this way. It's pulling the air fuel mixture in. And then there is an intake valve there. The outtake valve is closed. And the next step, the fuel mixture is compressed. So the piston is going up, right? Pushing in. So the gas is compressed, creating potential energy essentially. Then all the valves are closed to increase the pressure. And then the next part, there's an explosion that happens where the spark plug is lit, right? At least in the old days. Nowadays, it's all electronic. But anyway, an explosion happens. Of course, that creates a lot of energy, which dramatically expands the air fuel mixture and pushes everything down, right? That's that part there. And that does the work. So that turns the wheel and so on. And that's the step where the work happens. And the next step, of course, is just to get rid of the exhaust gases. And this whole cycle repeats again. So this is also an example of a heat engine. Okay, but just to think about something slightly different. Oops. Now, we can also think about direct conversion systems, which is mostly what we are interested in. We want to take light, convert to electricity, right? This is what we are interested in from solar cells, or solar thermal systems and so on. You can also think about it from light to fuel, which is photosynthesis. There are some biofuels, where you don't necessarily, you use bacteria or something like that to convert So algae is a good example, right? It converts sunlight into some sort of fuel that you can extract oil from. You can also think about hydrogen generation. Hydrogen is a fuel, and this hydrogen is generated by electrolysis of water with a catalyst. And the energy for the electrolysis can come from light, and the hydrogen is a fuel. So there are many examples of that. The fuel to motion, of course, we just saw. So that's pretty straightforward. Oops. And yeah, so those are examples, but we should also be aware of the efficiencies. The efficiencies will come to what limits them, but just to give you get some order of magnitude, electric generators, which go from mechanical to electrical. So again, is the opposite of the motion, right? It's about 80%. Electric motors, which is the cars and things like that, is like an electric vehicle, can be over 90%. So they can be very efficient. Light to heat can be greater than 90%. Chemical to heat can be greater than 90%. So the efficiencies can actually be quite high, theoretically at least. Now, what limits them? What limits the efficiency is what's called the Carnot theorem. Now, we'll look at this kind of in a very cursory manner, but to say in summary, the efficiency is limited by this expression here, 1 minus Tc over Th. Now, Tc is the temperature of the cold part, and Th is the temperature of the hot part. So what you can think about in this equation is that if I make the temperature of the cold part and the hot part the same, that means it becomes 1 minus 1. I get 0 efficiency. I cannot do any work. So I need to separate them somehow. So remember, think about the paper we talked about where they were trying to cool the building by utilizing the coldness of the space. So the difference in temperature on the Earth, surface of the Earth, and the coldness of the space is what they're using to do the work. If there was no difference, so for instance, can you do this in a planet that does not have an atmosphere? You probably can't. There's a small difference because the thermal mass of if it's a rocky planet, the thermal mass of it will probably heat it up a little bit. But if it's far away, it probably is not. Anyway, yeah, you have a question? So you can also think about, of course, light to electrical energy. The same limit exists in any heat engine. It doesn't matter you're trying to go from light to heat, light to fuel, light to electricity, or any other form. Everything can be related to this fundamental limit. So that's actually important. And this limit comes from thermodynamics. So let's take a kind of a quick look at this, basic thermodynamics point of view. Now, the first law of thermodynamics is an energy conservation principle, but it's a little bit different than energy conservation. We'll see how shortly. But the basic idea is that if you have a closed system, you put heat into the system, you remove heat from the system. Think about a refrigerator. The difference between them is the work done by the system. Common sense, right? So that is also thought of as changing the internal energy of the system. So in this introduction of this concept of internal energy is what distinguishes the first law of thermodynamics from the conservation of energy principle, as some of you probably already know from your undergraduate classes. So we have to see what that means shortly. The second law of thermodynamics, of course, is a bit more abstract. It essentially says that the entropy of a system always increases. Okay, delta S is always positive. S being the entropy, delta S is the change of entropy. This is very profound, and this actually is related to the point that we derived a few lectures ago, where we said that the concentration of light is how much you concentrate the light is inversely proportional to the acceptance angle of a concentrator. So if you remember, the concentration factor was in a 2D system was proportional to 1 over sine of the theta. This actually comes from this. Okay, we'll see that later on, but just keep that in mind. Now, let's dig a little bit deeper into each of these just to understand. But I should also point out that second law of thermodynamics is very profound because it also affects all kinds of weird things like the direction of time. So the fact that the universe is actually expanding, the fact that, you know, if you drop a, actually the two interesting examples which are relevant. One is if I open a bottle of perfume on one end of the room, given enough time, I can smell it at the other end of the room. This is, of course, a consequence of this law, the second thermodynamics, because, and osmosis and so on, right? Because I have a very high concentration of perfume molecules on one end, very low concentration everywhere else, it will diffuse. And that diffusion increases the degrees of freedom the molecules have, which is an increase of entropy. Entropy is a measure of the degrees of freedom of a system or measure of information in a system. That's a modern way to say it. Of course, these all come from statistical physics, so these are all statistical quantities. But today, when you learn this in physics, actually taught, I don't know how it's taught actually today, but in most papers, entropy is really defined in the context of information. And the second example has to do with time. So if you drop a coffee cup, it breaks into little pieces. The opposite doesn't happen. So that's the arrow of time, and people get older and so on. The universe expands. This is also defined by this fact that the entropy is always increasing. Anyway, we are going a little bit off topic here. So let's dig in a little bit into the first law of thermodynamics. So a little bit of words. So again, the basic concept is that the internal energy of a system is the difference between the heat input and the heat work done by the system. So the increase in the internal energy of a closed system is equal to the total of the energy added to the system. So the net energy of the system. So in particular, if the energy entering the system is supplied as heat, and if energy leaves the system as work, the heat is accounted for as positive and the work is negative. So Q minus W. Now, so all of that is relatively common sense. Now we need to understand what does the internal energy mean. In the case of a thermodynamic cycle of a closed system, it returns to its original state. Now, what does that mean? Remember in the heat engine, we talked about a cycle. So in the internal combustion engine, you had the 4 strokes. You came back and repeated it. So that's coming back to the initial state, okay? So when it returns to the original state, the heat Q in supplied to the system in one stage of the cycle minus the heat Q out removed from it in another stage of the cycle, such that the total cycle is built. Plus the work done plus the work added to the system Wn equals the work that leaves the system Wi. So if you do a full system, delta U of the full system of the full cycle, that must be 0. In other words, we can write for a full cycle, the heat in minus heat out plus work in minus work out is a net work in the system. And the internal change in the system energy, internal energy, is the work in minus work out, or the work net. So this is a little bit abstract now, but if you think of a completely thermally isolated system, we'll talk about what adiabatically isolated means in a second. The change of internal energy of the system can only be the result of the work added to the system, because the adiabatic assumption is that there's no heat going in and out. Not so, we'll make it more concrete shortly. Now, conceptually, what does this mean? It is essentially conservation of energy, and then there's the new concept of internal energy. Now, what is internal energy? Internal energy means any system has constituent parts. If you take this bottle, it's comprised of atoms. And as long as it has a temperature greater than absolute 0, those atoms are always moving around. They're never at a standstill. The kinetic energy of these atoms, plus the potential energies associated with the Coulombic interactions between the different particles that make up this matter, create what's called the internal energy. So the internal energy of a system is simply a measure of the degrees of freedom that are inside the system, inside the constituent particles of the system. So again, it's a total energy. You can think about it as a combination of kinetic energy, potential energy, and the system internal energy. So that's basically what this is. And the new concept here is the fact that we are defining an internal energy. Now, I won't go into much detail here. It's the fact that there are microscopic constituent particles which have their own internal kinetic and potential energies, which are essentially plugged all into one term to define the first law of thermodynamics. Now, this can also be chemical potentials and so on, but we're not going to worry about this for that level of detail for the purpose of this class. Now, we also have to be very clear what does work mean? Work is simply a process of transferring energy into and out of the system. Think about the refrigerator, think about the motion in the case of the internal combustion engine. Okay, so that's another thing to think about. In the case of a solar cell, that work, as you will see later on, will be the kinetic energy of the electrons, which of course, as electrical engineers, how do we measure it? We measure it as current, because motion of electrons. Current multiplied by the potential over which the electrons are moving across gives you the power or the work done by the solar cell. So all of this will connect to the solar cell as well. Now, of course, flow of heat is a form of energy transfer. We all know that. So now the second law is, of course, a bit more abstract, but just you should be aware of these things. First of all natural processes are irreversible. And this is the consequence of the second law of thermodynamics. Entropy was only increasing. If you want to decrease entropy, which happens, by the way, in the context of reverse osmosis, we talked about it. You're working against the second law of thermodynamics. You have to do work on the system. Okay, so it's a good example. And of course, the other thing we have always seen when we talked about, for instance, the CPC in a vacuum and so on, temperatures always tend to equalize. That is also a consequence of the second law of thermodynamics. Again, that is similar to the diffusion of the perfume particles from one corner to the other corner. And that's similar to the equalization of temperature. Analogous, let's call it. So again, just to think about this, when two initially isolated systems in separate but nearby regions of space, each in thermodynamic equilibrium with itself, but not necessarily with each other, are then allowed to interact. So bring them such that they can exchange energy, they will eventually reach a mutual thermodynamic equilibrium. The sum of entropies of the initially isolated systems is less than or equal to the total entropy of the final combination. So in other words, the entropy of the entire system has now increased. They can be equal only in the assumption of the adiabatic assumption, which of course does not, it's an artificial assumption, it doesn't actually happen. It's not so important. Entropy of a closed system only increases with time. Now let's think more concretely. And this is really where we want to think about those abstract concepts and try to apply it here. Now, we'll start with a very simple idea of the heat engine and the heat cycle. So the heat engine here is similar to what we have seen before, the refrigerator and so on. We have a hot source at some temperature, TH, which is putting heat into the system. The system is doing some work here. And then it's letting some heat out of the system. Like the refrigerator has a hot part, and there's a compressor which is doing the work. So the source there is the compressor. So if you, for instance, if you have a solar concentrator, the source TH would be where the absorber is in that case. Now, what Carnot's theorem tells us is that this efficiency is TC over TH. We'll apply this to the solar concentrator case shortly. Now, Carnot's theorem says that all irreversible heat engines between two reservoirs are always less efficient than a Carnot engine operating between those two reservoirs. And the efficiency of the Carnot is given by that expression. Now, the Carnot efficiency can be thought of from the context of a gas system in a pressure volume diagram. So you have seen this before, but let's go through this very quickly. So it's a cycle, first of all. So it's kind of an expansion compression cycle, since we saw in the refrigerator. So here, of course, we are looking at ideal situations. It does not exist in reality. It's not such beautiful curves like as described here. So we'll start here. So first of all, you have the isothermal compression, which is shown by this red curve here. And what does that mean? That means the temperature is fixed at T naught, okay? TC, sorry, so that's the cold part. And then the material is compressed, the gas is compressed. That is a situation when the heat is drawn out, okay? The heat is drawn out of the system. Then you have an adiabatic compression that has happening here, this part of it, where again, the volume is decreasing, but now the pressure is increasing much faster. You're allowing the temperature to actually go up, okay? You're not maintaining the temperature. Now, of course, we didn't talk about physically how we're doing it because that's not important. We're abstracting it into a cycle. And this, of course, physically happens because you get work done by the system. Then once you're here, you allow the gas to expand. In this case, there's an isothermal expansion happening at a particular temperature, TH, and heat is brought into the system. That's the QH. And then you have an adiabatic expansion here, where you allow the temperature to change. It cools down as it expands. So you have 4 stages to the cycle, but the idea is that it's a cycle. It ends up where it started from. And the efficiency is defined by that, by Carnot. Now, this is the maximum possible efficiency of heat engine. So if I were to ask you, what is the best efficiency that you can achieve from a solar cell? The answer would be what, actually? So let's stop here and think about that for a second. What is the best efficiency I can hope to get from a solar cell? %20 is practical efficiency, but let's ignore practicality for the time being. Let's assume, we're not limited by engineering or anything like that. From a thermodynamic limit, what is the best I can hope to get, or you can hope to get? That would be what most people would guess. But Carnot tells me no heat engine can be 100%. Now, actually, tell me, when can this be 100%? Yes, that's a very important point. And at 0 Kelvin, you can be 100%. But what does 0 Kelvin actually mean? Nothing is moving. Now, that is also from a, you can think about this from a quantum mechanical ground state. So think about something that is in its quantum mechanical ground state at 0 Kelvin. Now, for a macroscopic object, this has never been done before. It's actually not even clear it's possible. It's actually a very important area of research today. So let's put that aside. The 0 Kelvin is theoretically, it's not clear if one can actually reach 0 Kelvin, even theoretically. So we don't actually know for sure. There's a bunch of work going on. In fact, I have a collaboration. We're trying to do this kind of stuff. But let's put that aside. Let's think about a solar panel on your roof today. And let's ignore any engineering limitations. And you have the sun. What is the highest efficiency I can get out of the solar panel? I'm not looking for a number. I'm looking from your understanding of what we have talked about in the last few slides. Correct. So what is my TC? It'll be room temperature, more approximate. Yeah, 300 Kelvin, something like that. What is my TH? The surface of the sun, because that's my hot. This is my cold, and I'm trying to do work in between. Ideal situation. So you can plug in those numbers, and I don't know what you'll get because I haven't done it, but you'll probably get something a bit more than 99% because the surface of the sun is 6,000 Kelvin, right? 1 minus 300 by 6,000 is probably close to 1. Very back of the envelope, right? This is, of course, not really possible. We'll come back to this point again in the second half of the semester when we talk about spectral splitting. That will relate to this question that I just talked about. Okay, next let's take a, and you should also be aware that there's something called a Stirling cycle. It's a different engine, but not terribly important. It is something that can come close to or equal the Carnot efficiency, but since we are not a thermodynamics class, I'm going to skip that. So this is really probably the most important slide I want you to kind of think about as part of this part of the lecture, basically all these concepts, bringing them together. Now, before we think about this, the idea is to compute, in the ideal situation, what is the efficiency of a solar thermal collector. So let's say you design a CPC or parabolic concentrator, whatever, it doesn't matter, we're going to abstract it out. Let's try to calculate it, okay? Now, what are the different terms that go into play? First, so Carnot is what will, so I should draw, I'm going to draw some sort of collector here. He's collecting the light. The light's coming in. I'm going to collect it. And I have an absorber here. And this absorber is doing work. So the question is, from this input to this output, what is my efficiency? This is the question we're trying to answer. So that when the absorber does this work, this step here, this is where Carnot comes into play. Right? That's the last step. So that's where this efficiency comes into play. Okay. Now, so that's easy. So, you know, we just need to know the temperature of the cold part, temperature of the hot part, and then divide. Okay. Now let's think about the collector itself. What is the efficiency of the collector, which is this step? You have an absorption, heat absorbed minus heat lost, divided by the incident heat. That would be the efficiency, right? So I'm going to erase this stuff. Let's think about this for a second. You have heat absorbed minus heat loss. So there's always some loss. We're going to talk about radiative losses and some incident heat. Okay. So now let's try to see what these are. Heat lost is easy. We have done this before. It's simply Stefan Boltzmann Law. If we assume there's only radiative losses, it's going to make simple assumption. So Stefan Boltzmann Law is simply the area multiplied by the Stefan Boltzmann constant multiplied by the temperature raised to 4. This TH is the temperature of, well, okay, we are assuming here that TH should be the temperature of the, in this case, I'm trying to think. Yeah, maybe it should be TC. Yes, I should think that's a mistake. I think these two should be TC. Let's come back to that. Okay. The temperature of the collector. So remember, the collector, which is the optic, is collecting the light, is also getting hot. It's not 100% efficient, so it absorbs some energy and heats up. It's also going to radiate energy out. So that's the loss we're talking about. So that's its area, A, multiplied with Stefan Boltzmann constant, its temperature raised to 4. And I added a term here, emissivity, which we saw in that paper from UCLA we talked about. It's just in how efficiently does it emit light. We're going to assume it's 1 for the sake of most of our cases, but just be aware that some things emit light better than others, as we all know, right? Like exactly like wood, the conductivity of wood is very different than that of metal. The emissivity of wood would be very different than that of metal. So that's the loss term. The incident energy, of course, we all know it's the intensity of the solar radiation, watts per meter squared, times the area, times some concentration factor, right? We're trying to concentrate the light. So, so by the way, let me go back to this picture here. We have I have my absorber, and I'm going to say the area of the absorber is A. This is the collector. The area of the collector is A multiplied by C. Oh, actually, yes, that's right. So this lost is actually from the whole system, not just the collector. So I think it's consistent then. So now I can put it all together to estimate the efficiency of the collector. It is simply one. So I'm taking this and putting it here. And I'm assuming that the absorption is 100%, a very simplified assumption. So that's why I get this. This and this are the same, so I get that one. Minus everything else is just simple algebra, right? You're okay. 1 minus sigma epsilon t raised to 4 divided by c times isolate. So now let's think about what this means for a second. And then before we do that, to get the total efficiency, I have to multiply the efficiency of the collector with the Carnot efficiency, because the collector is simply collecting the light. Then the absorber has to do some work, which is a Carnot efficiency comes in. So that's what you put them together, right? So now let's think about this for a second. So, and that's where the plots come into play. Here, if you think about this, first of all, you notice that the C goes in the denominator. This is the concentration factor, right? So there's a negative sign here. That means if I increase C, this term will increase. The denominator increases, this term decreases, but there's a negative sign, so the whole term increases. So I can improve efficiency by increasing my concentration factor. Kind of intuitive. Second thing you'd notice is the effect of this TH. You'll notice, of course, here, if I make my TH as high as possible, which is what I want, this whole term goes closer to 1 as possible, 100%. I want to make that as high as possible. But this is working against that, because that's the radiative losses, right? There's a negative sign. If I make that too high, I'm going to lose energy. So there's an optimum because of these two terms. The Carnot efficiency demands I make my as hot as possible, but the radiative losses tells me I cannot do it indefinitely. That's where this curve comes from. So this is a very simple plot. Let's look at just one of them. That's this black plot. Actually, I should use this. This black plot shown here is the concentration factor is 10. Okay. And what you see is that as temperature increases here, of course, at temperature 300, my cold temperature so I'm assuming this absorber is doing work. First of all, I should be very clear about the assumption onto something that is at room temperature, TC. So my absorber is at TH. Okay, so that's my heat engine part of it, right? That's what I'm trying to abstract out the Carnot efficiency for. And that at 300 Kelvin, because my TC is also 300, of course, I'm not doing any work there. The temperature, my efficiency is 0. As I increase the temperature by concentrating light and heating up this absorber, my efficiency starts going up. It goes up until it reaches an optimum where after which my radiative losses start to dominate and starts going down. Okay, so that tells me if I have a solar thermal system, that's the temperature I want to be operating at because I will get the highest efficiency. Of course, we've made lots of assumptions here, but just to give you a conceptual, intuitive understanding. Now, can I increase it further? The answer is yes. I can increase the concentration factor. So I can concentrate to 50x. So this is 10x. This is 50x. I can get a higher efficiency. And go to 1000x. So this is the reason concentration factor allows you to get higher efficiency from systems. However, there are trade-offs, as we all know. If you increase the concentration, the CPC gets more complicated, your optics more complicated. You have to track the sun because your acceptance angle is smaller. So they're all trade-offs. Next, we'll look at two examples of how these trade-offs are actually met. First, of course, these are very important in solar thermal plants, and we'll come back and look at these in a little more detail later on. There are two examples shown here. One is with the what's called the Sandia dish Stirling machine, where what they do is they make units like this and then deploy them in large areas. So that's an example. Has a it's a very large concentration factor. First of all, it's a parabola, reflective parabola, and the heat engine is put at its focus. High concentrations, 2000, very high operating temperatures, several hundred degrees, large installations. Where the idea is to make them modular and be able to essentially scale them up. They're expensive. The other architecture, of course, is what's shown here, and we'll see this in a little more detail later on, is to use heliostats, essentially large arrays of highly reflective mirrors, which is simply concentrating the light onto a tower, which is shown here. This is a system from Spain, which is probably the largest system in the world. I'll come back to this later on, and that runs a heat engine. So the purpose of this is just to focus on the optics, but the optics is creating the hot part, and then the hot part does the heat engine. So I just wanted to emphasize the TH for now. Okay, so I have two videos that we can look at, but before, actually, I'm going to play it. And then while I'm playing it, I want you all to think about what are the problems that you can identify in both these approaches. I'm going to play those two. And then I'll ask you. So and you can discuss. You're welcome to discuss now as I play it as well. Let me unmute this and. And for those of you on Zoom, it's the same thing. So feel free to think about what problems you identify in the examples we looked at. And you can put it on chat, or you can, of course, speak. Any thoughts? I'm going to ask you. Sorry, I can hear. Yes, that's a good point. Yeah, it's a very good point, actually. Kelsey mentioned the molten salt will lose heat very quickly. That is the radiative losses we talked about. Of course, not on the, and that's the absorber, the TH we talked about. And of course, insulation is important. Of course, also molten salt is incredibly corrosive. So you need to have a material science problem, how to actually store it. Right? I don't know enough about it, but it's definitely an important problem. The salt. Mm-hmm. Yeah, you don't need to burn it. What you do is you just put it in contact with water, it'll become steam. Yeah. You have to go through another, yes, that's a good point. Yes, exactly right. So every time you do the conversion from one type of energy to another, you're going to lose energy. So definitely, it's a good point. In other words, what you're saying is if you concentrate it right onto PV and use electricity, that might be better. Now, the reason they don't do it, by the way, is because unfortunately, there are two problems. One is if you concentrate this much on PV, the efficiency of silicon drops dramatically. There are some materials which might work, like gallium arsenide and 3,5 and so on. We'll talk about that later on. But they tend to be very, very expensive, so really hard to scale up. So and the second problem is to scale up, the cost becomes very high. That's a good point. Anything else? Of the absorber, you mean? You're talking about the absorber, right? Yeah, that's a good point. Yes. Yeah, now I see. I didn't think of that. That's a good point. What you're saying is that the incident angle of the light from the heliostat will be at a weird angle to the absorber. And as we saw in a previous lecture, that angle, you have the cosine theta loss. You want that to be as normal as possible. That's a good point. I didn't think of that. So how would you solve it? I guess you kind of design it to, yeah. I mean, you can do it round, but round doesn't completely solve it. You still have the angle. So you want to try to, if you had a way to adapt it, that would be good. Anything else? That's an interesting problem. That's a good point. You're losing energy. That's a good point. I didn't think of that either. So yeah, any surface, as you know from the geometrical optics lectures, will reflect some light. So even a small percentage of reflection over a huge amount of energy shows up as very bright. So if you ever drive by the Ivanpah outside Las Vegas, it's actually really close to I-5. So sorry, 15. So you can actually see it. It's really, really bright, and you are losing a lot of energy. Anything else? Can you speak loud? Yeah, that's the idea. Yes, can it get us? Yeah, that I think they can. I don't know exactly the numbers in the, but that you don't think from a temperature perspective, although it's related. You think from a power output perspective, right? Certain megawatts. So megawatts is in the order of smaller coal power plants. So I assume they can be. It's a good question. But there is two important problems that we didn't talk about. One is wind loading. Think about the mirrors kind of, they have to travel, track the sun and so on, right? What if there's a windstorm? You get destroyed, right? It's a very important problem. And there are people trying to deal with this. and really difficult problem to solve. The second thing is, there is always this trade-off. If you think about these systems, where do you think the most cost is? Bill of materials, forget the labor and so on. If I just look at this, where do you think the most expense, where am I, if I were to invest in this, where will I put in the most amount of money? Oh, yeah. Yes. Yes, very good points. Yeah, I will come to that in a second. Let's see if anyone can guess where the cost comes. Yeah, you're close. I would say the entire heliostats, because there's so many of them. That's is something like over half of the cost of such an installation goes to the heliostat. So improving the cost of a heliostat can make a huge difference in the entire system. And there, you know, I had a friend who worked, he's still there, at Google X, who was working to solve this problem. Interestingly, Google has an interest in energy. So just to, Brian mentioned a couple of points. One, he said that you need large area with no obstructions, no shadowing and so on, which actually reminds me, you have to arrange the heliostats such that when one tilts, you don't want it to shadow the one next to it. So the arrangement of the heliostats is actually very important. And if you look at Bill Gross's TED Talk, which I posted in one of the previous lectures, one of his main things that they developed is some algorithms which allowed them to place the heliostats very carefully based on the terrain and so on. Not a simple problem. And the other thing, they have to be kept clean, of course. And so, you know, usually in the desert, it's problematic, so you wash it off. So if you have solar panels on your roof, they tell you to wash it off with a hose. That's a manual thing, right? To think about doing it over tens of thousands of heliostats, painful. So robotic solutions. So people are working on innovations to do all that. Okay, so yeah, I want to take a short break. Actually, no time for a break, so we'll go on. But I just actually I'll come back to this. So we have one more topic to cover. So any questions before I move on to the radiometry, photometry side of things? I was going to talk about the presentations and why kind of I ordered it this way. So maybe I will mention briefly. So the idea was to, just so you see the full picture, you did the literature review to build foundation. Then you're going to do the innovation, which is the initial analysis. You have the problem statement, you have the solution statement. That's kind of like your initial foray with the brainstorming. Then right after fall break, you're going to do a little bit deeper analysis, like simulations, maybe you'll build something, whatever. And then the Thanksgiving week, you have a demo day. Now the demo day is kind of in quotations because you may not actually build something, which is fine. Demo your solutions, can be simulations, whatever, wire grid models. And finally, commercialization. We'll talk a lot more about this actually right after fall break. Okay, now we should, let's see. Oh, sorry, this.